So here I'm sharing the screen to our demo environment blueprint. This is a natural deployment. It'll be similar for AWS. The overview page shows us the environment from three different lenses: efficiency or waste, performance or latency, or orchestration. Now, efficiency and waste is the cost in dollars I'm wasting in my environment, unhealthy spend. I'll go back to September, full month. The performance is really the time to insight component. How fast am I running my jobs? And the orchestration is really the effort of scheduling all my workloads that obviously help me with both the other two components, time and money. So how do we go about solving these problems? Now the tool shows me a summary. Let's pick efficiency and waste because it's easiest to tackle, right? And it comes from three different sources: pools, idle VMs in pools, idle time in clusters, and over provision workloads. If I go one level deeper into the tool, I'll see the cost per workspace breakdown, distribution by feature, job cluster, all-purpose compute. The sixth item in the list is idle VMs. We typically see high values here with every customer we talk to that using pools. They're using pools to reduce the startup time of workloads so they can have that time to insight, right, component optimized. But if it's not properly configured, it creates a lot of waste in the number of idle VMs, which obviously is associated with dollars. So this is where we look on day one to see if there's issues with the pool configuration. So let's dig into that, the first component. If you go to the workloads area, there's workflows, all-purpose cluster, Delta Light table, SQL warehouses, and pools, right? So we'll start with that. And I see that I have a list of pools in this workspace. I'm picking this one, executors. And I know that, like say, for example, if I did this, I found a spike, one of these days, right? The tool will find the spikes automatically for you. I can drill into that, zoom in on the screen, and really find what the issues with that pool and the usages of that pool by all the concurrent workloads during that time. And I see that solid colors are clusters, workloads. Could be all-purpose clusters or job clusters, or DLTs for that matter. And then for each one, I have a auto-scaling timeline. It's the number of VMs in time. Right? On the left, on the y-axis, I have the number of VMs. X-axis is the time components. I have three workloads starting. I have the name of the cluster, the job, everything I need to know about its start, end, and how long it took, how many VMs it required from the total. And what I'm seeing is if I have too many clusters asking for VMs in the same time from the pool, basically in contention mode, the VM count increases. The higher the VM count, the higher also the idle VM count. And that's because now the pools are configured with a timeout, with a shutdown timeout. VMs are returned to the cloud in 12 minutes unless another cluster picks them up. If no other cluster picks them up, they're going to stay idle in the pool. No, I'm seeing here a period of 4 minutes, 45, 12 VMs, just completely idle. Nobody picked them up because the first cluster only started later, right? So how do we reduce the waste? Now this shows me how I can reduce it with the three approaches. One is to change the configuration of the parameters of the pool, the minimum idle and the shutdown timeout. Another one is to reschedule, to reorchestrate your workloads so that you reduce the VM count. Basically, shift them to the right, delay them a bit if you can, if your business allows you to do that. And then you reduce the maximum VM count, which then naturally reduces the idle VM count. Or relocate your workloads in another pool, like create another pool. It's really easy to create one and move them over there. That's how you basically reorchestrate and you reduce again the VM count. All-purpose cluster should not be in the same pool with job cluster, for example, because of different usage patterns, right? So those are my workloads. That's the approaches of how to reduce the idle VM. Now, if I click on one of these workloads, like I said, we stacked up together all the scaling timelines of each cluster. That's how we know how many VMs were used. And if I go into the detailed view for this job run on September 28th, I have this auto-scaling timeline available, and this shows me how my cluster consumed VMs from the pool. Now this is the segment of 4 VMs for the duration, start, and actually even the cost of that. So for 10 minutes, 4 workers, 4 VMs for the cluster nodes, and that was the cost. The auto-scaling timeline in this case shows me there's a bit of a change in VM count. Every change in VM count, every auto-scale event here is going to cause some delays. So I have to look back at my workload and see if it's actually really useful to have auto-scaling, or maybe I'm just better off with a flat line, fixed size cluster, because most of the time these small two node segments are like 45 seconds, almost like it's not even worth to keep auto-scaling in this case, right? What we've seen bigger problems here is we have workloads that are calling out external services. Databricks cluster is up, calling another workload from Snowflake, BigQuery, or another compute engine, or calling external APIs that are taking a long time to build something, right? Or even doing something on the driver. Maybe all of a sudden I collected my data on the driver. I'm doing something on the driver, pandas data frame workload. Obviously, the cluster will see a flat line here in the auto-scaling timeline. That's an anti-pattern for using the cluster, right? External services should be reorchestrated in a way that when you use a cluster, use it and then decommission it. So that's an anti-pattern that the auto-scaling timeline picture will give us. Calls to external services, they should not be orchestrated mixed with the Spark workloads. They're supposed to run in a cluster, right? So that's the auto-scaling timeline. Back to the type of ways that we have in an environment. I talked about idle time in all-purpose clusters. And if I look at this, I see the all-purpose clusters in this workspace, and I see the active versus idle time, right? How much is that all-purpose cluster up for, and how long it's actually being used by workloads. And it looks like the 77% of this cluster, 19 hours, actually was idling. Idle means there's no Spark activity in the cluster, or the CPU is lower than 3%. That's configurable, obviously. And immediately, the first step to solve this problem is you're going to get them in the incidents area, and if I'll filter by all-purpose cluster, I'm getting all the incidents, shutdown timeout above threshold, right? So the easiest way to fix the idleness in the cluster, all-purpose cluster, is to reduce this shutdown timeout, right? At the end, it's spending 45 minutes every time it started before it stops, when really the minimum data breaks is 10 minutes, and the configured threshold in LHO, you can change that, is 15 minutes, right? So the easiest way to reduce idle is just to look at these numbers. We've seen default numbers in the thousands of minutes, right? So that's not a good thing. So that's how you reduce it's the easiest way to reduce the idle time in a cluster. There's other ways. For some other time, we'll have another follow-up with those. Over-provision workloads, I want to touch on that. So if I look at my workloads here, let me pick something from last month. This demand forecasting multi-site job. I'm seeing that it has 7 incidents. It's a multi-task workflow, 2 tasks. Each task has 3 nested notebooks. I'm going to look at the incidents because they show it to me. So I see they have 2 clusters basically. There are 2 clusters used for this job run. Very likely each task runs in its own cluster. And I have more than one event. I have cluster CPU over-provisioning, memory over-provisioning, driver memory. So there's a lot of issues with this. You have the explanation here, the thresholds that were exceeded, the CPU or the memory amounts. And then you have recommendations on how to fix that immediately. And then, for example, for the first set of problems, we're telling you that we should downgrade your driver to an instance of this type, right? Standard F4, 4 cores, 8 gigs, and so forth. So we give you the list of instances that you can use to basically reduce that over-provisioning. Over-provisioning means too much CPU or too much memory allocated to your cluster. And you can see that immediately in the data points. I'm picking the first task, and I see that there's only cluster memory, only at the maximum 4.27%, right, of that cluster. Let's see, that's not a good idea. It says 14 gigs on the nodes, 6.5 on the processor and the JVM, and I'm only using 276 megabytes. Clearly over provision. You can obviously go and use a much smaller instance type and save a lot of money in the process, right? So that's the data points are available here for cluster memory and CPU. And let me pick another example. I'll show you what we have a full cluster, the train job. I believe we'll have that. Yeah, this one. So let's look at the CPU for this, the cluster memory. There we go. So this is a multi-node cluster. You have, each one of them is 8 gigs. You have the memory on each one of them, on each node, the max and average, but there's also the full histogram of this cluster, both memory and CPU data points available in the LHO database. that if you want to look deeper and find out if you have, a CPU bound or an hour bound job that can be reconfigured differently, right? So it will help you with that part of the optimization process. So that's what I basically wanted to show you in terms of how to fix now the efficiency or the waste part of your environment. Reach out to find out more. And for now, this concludes the technical deep dive of this presentation. Thank you so much. Back to you, Heather.